So today, in the first class, I'm going to continue about OpenMP a little bit. Maybe will be an advanced subject. So just I want you to familiarize with this advanced subject and to see what OpenMP can, except that was before. Okay, and in the second class, I think, I expect that you will show your undone codes. Yes.
For homework 4.
Yes. 4, 3, because the deadline for 4th homework is, as I remember, yes, next class, 6th of November.
Oh,
December.
Wait, so it's next, not next? Not on the, how can I say,
No.
13th? Wow, the 6th.
What, today? I just don't remember.
No, so I think it's the 6th of December, but I thought it was on the 13th of December. We should have that one.
No.
Okay.
December 6th. And answer your questions and so on, just regular work. Okay. So what is the next? We have, let's just remind, OpenMP is the some library to write and launch your programs on shared memory machines. Yes, and we have discussed that OpenMP uses directives, some directives, and these directives can be divided in 3 categories: to describe parallel scope, where your program will be parallel, or where it will be single, not single, sequential. Some directives describe work distribution. We have discussed about work distribution in for loop, when the steps in for loop can be divided into several threads, and each thread executes its part of this loop. Okay, and some synchronization, which can be at the end of parallel section, at the end of loop, implicit synchronization, or it can be explicit synchronization when you just write or define critical section, when you work with shared variables. Yes? Do you remember about this? I have just repeated. Okay. So now I want to go forward in work distribution. We have discussed for loop statement where why we can use directives for loop. How do you think? When can we use directive to parallelize for loops? When? You see some for loop statement. For loop, there are a lot of operations inside this for loop. Okay, how do you think? When can we use OpenMP directive to divide this for loop between threads?
We want to pass a lot of data at the same time. Suppose it's an array and we want to fast some of the array to one thread, the other thread, the other thread. That's we use a for loop to do that. That's one of the ways why we need a for loop to threads.
But these operations inside for loop should be some okay. So these statements inside for loop should be some conditions. Which conditions? So to parallelize something, that means you can execute these operations at the same time. Those operations, these operations some conditions. What are these conditions? How do you think?
Maybe a condition if a certain value is reached, then we change the thread that we're going to send to, maybe something like that.
Not yet. I mean, these conditions are not concerned to OpenMP itself. They are about parallelism as a whole, in general.
Maybe the condition if the thread is overloaded, that there's too much data passed to the thread.
No other opinions? No opinions. Maybe these operations should be independent to each other.
That makes sense. Independent, yeah.
It should be independent to each other. But so in this case, we can divide our operations between threads, between processes in MPI, and so on. And we can do this operation simultaneously. Yes? Okay. But what if we encounter it with operations that are depend to each other?
Then we're going to encounter maybe a deadlock.
Not deadlock, it is okay. It will be hard to parallelize them. Maybe there is no, maybe it will not be any ways to parallelize. Maybe yes, maybe not. I don't know. It's about algorithm, about our task, and so on. But maybe, for example, I will show you. What I want to say about dependence or independence of data in operations and so on. For example, let it be. А вы можете вывести, кто присутствует? Не чат, а кто присутствует. Есть там кто-то? Let it be arrays A, B, and C, for example. If we want to calculate something, for example, for I and Ci, equals to A. So how do you think inside for loop statement these operations independent or not between steps?
Well, they're going to be, maybe you can decide that they're going to be on the same iteration. So if I equals to 0, then everything is going to be the first element in the array. But as in, I don't know, values themselves, probably they're not dependent.
I think they're dependent.
Yeah, so they're dependent.
No, yes, if we consider, for example, I equals to 1 and I equals to 2, for this number of numbers of counter, these operations will be independent. So we can divide our loop into parts and so on. But what if, for example, for I plus 1 equals to 2 times AI. So what will be in this case?
Well, now we're maybe showing some dependency because we're using the previous value, therefore it's independent.
So can we divide this for loop into parts and execute these parts simultaneously?
No.
No. So it depends. Using directive OMP4 is dependent on the fact will the operations inside this loop be dependent to each other or not. If they are independent to each other, so we can divide. But if there is a dependence, some data dependence, so we cannot. And the question is, can we make parallelization in this case using OpenMP? It seems no, yes? But if, what will be the same problem? Why is it so? Okay. For example, what will be if we have 3 for loops? So the same A, B, C arrays, and first loop for is for array, or it can be inside. Firstly, let it be inside just one loop. AI, BI plus 1, something like this, 10 plus BI, and CI plus 1, I don't know, CI, times CI, let it be like this. So can these operations be parallelized using OpenMP? Somehow.
Yes, sir.
How?
The reason I said yes because you wouldn't be asking the question if you couldn't. No, but there is a first way.
We can calculate A, B, and C at the same time.
Other opinions?
Maybe to get the value from, let's say, one thread calculates the I plus 1 and it gets the value from the thread simultaneously. So we wait until we get an answer from a thread and then we calculate it.
Maybe. Who wants to say something more? Okay, for loop is right. It made correct solution for this task. So it seems that this operation, these three operations are independent to each other. There is a dependence inside every operation, but these lines are independent. So we can divide, okay, we can create 3 for loops. For example, first for loop is for first statement, I plus 1, like this, yes. Second loop, and third. Something like this, yes. And in this case, we divided first one loop into 3 parts, and inside every part, 3 independent loops, and inside every loop there is a dependence. So every loop we cannot divide into parts, but these 3 loops we can execute simultaneously. So OpenMP has the ability to do this, some ability, okay? And we consider this ability now. This was before, now. Firstly, I want to discuss a little bit more about some options or some directives for you. They are rather simple, so we will not stop here for a long time. First directive is pragma OMP single. That means this part of code will be executed just by one thread, and we don't know which thread will execute this part of code. First, with ID 0, 1, 2, it doesn't matter, just some single made as a thread. And similar to this is the directive pragma OMP master. That means this part of the code will be executed by master thread. Master thread has ID equals to 0. And there are several options for parallel part. I mean directive pragma OMP parallel, as you remember, and several options like first private, no wait, we have considered no wait, as you remember. Okay, first private, copy private, it can be last private. So what is this? So as you know, private means inside this every thread this variable will be private with non-defined initial value. Non-defined. First private will define these variables with the values that was in master thread. Master thread, the thread which was before parallel part. So every private variable inside every thread will have a value equals to value of master thread before. Copy private, if because of this part of the code executed just by one thread, that means this thread will have some value for a variable. Other threads will not have values inside these variables because they do not execute this part of the code. So that means somehow this variable has not any value. And copy private means that after execution by this thread, this new variable, this new value of this variable A will be copied to other threads, and other threads will have the same value inside their variables A.
So when we change this private variable A in the thread, it gets changed in the master thread.
In every thread, because this OpenMP single should be inside parallel part of the code, inside parallel section, and inside this parallel section there are a lot of threads. Okay, let I draw. Parallel part now, and this is single part. So it can be some variable. Let it be 10. And let here parallel and number of threads will be 4, for example, doesn't matter. And here will be a thread with ID equals to, for example, 2. Inside parallel, let this private A. Inside this parallel section, every thread will have their private variables. And by default, the initial values of these private variables are not defined. This thread with ID equals to 2 do something inside this single section of the code, and its variable A has value equals to 10. And here let it be like this: IDs 0, 1, 2, and 3, and A equals to, I don't know, 10. Okay, let it be questions. It can be zeros, it can be garbage sum, it depends on the compiler. And if we use the statement copy private, that means this value will be copied to other threads, and A inside every thread will be 10, 10, 10, 10. Okay?
There can be more than one single section.
Of course.
So what if ID1 changes another single section A equals to 5 and we copy private?
Let's see. Okay, we can see. Let's see. So will be, we can erase all these things. So we have S as a private, let it be S, and OpenMP single copy private s I don't know which one will be here. S equals to 10, for example. And let's, before this, we can pragma OMP barrier, and before this barrier we can print yes, I am thread number something, and print s equals to f, like this, and my ID here and s. So let's check. G++ OpenMP simple. So s equals to 0. Okay. Now we want to print here. Before barrier. After single. So you can see before barrier s equals to 0, and after single all variable s equals to 10. It's okay now. If I do not use this statement, we can see s equals to 10 just in 0 thread. Maybe let's make it bigger. Is it better? Okay. So you want to do another single like this, yes? Like this? Okay, copy private, we'll see. If I do not use here copy private, we can see that just one thread is executed this part of the code, thread number 0, yes? So what will happen? How do you think here? Why if we use copy private here and copy private here, we get all s equals to 5 in every thread, I mean?
Because when we call copy private, it means we're going to change all the values. So I guess it doesn't matter how many copy privates in the part. The last one is going to be the value for all the variables, maybe each thread.
Yes. Let's see in detail. So what does it mean? That means we can let's see even like this. Let's print the ID of this thread. Print first single. I am D, my ID, like this. Second Let's see. Second, every time, and we comment this line. So what we can see? We see that in the first section, in the first single part of the code, is executed by thread number 0. Yes? So what it is? Thread number 0 changes its variable a to 10. At the end of this section, it will be copy process to other threads, and other threads will have the same s equals to 10 and so on. So before pragma-omp single, every thread will have s equals to 10. So now we can see that second single part of the code is executed by thread number 1, this one, and it changes its s to 5. Because there is no copy private statement, that means this 5 will be inside just this thread number 1. Yes? And 10 will be in other 2 threads. So if thread equals to 1, s equals to 5, it's okay. And you can see that s equals to 10. If we uncomment this copy private, so s will be 5. Because we print here, where? Yes, after let's print like this second single and check values between two single parts. So after first. So after first single, we can see all threads have s equals to 10, and after second single, every thread equals to 5. Because at the end of every single, there is a copy process from one thread to another thread, and so on. Okay, so let's go further. A little bit with small letters, maybe erase, for example, this and make bigger. Okay, to realize this approach, this one, when we consider dependent operations, but like something like this. So we have some dependent operations and some independent operations. We cannot divide 4 loops, but we can execute these loops simultaneously. So how we can do this? There is one possibility to do this. To use pragma-omp parallel, OMP pragma section, pragma-omp sections. This directive defines some independent areas of your program. Inside this directive, inside this part of the code, can be several sections named as pragma-omp section. every section will be executed independently to each other. Which thread will execute some section is not defined. Some thread, it doesn't matter. So if a number of threads is greater than number of sections, that means some threads will be idle. If number of sections is greater than number of threads, that means some threads will execute several sections. Something like this. So in every in this case, in every section we can put our for loop with dependent data, and every section will execute different loops. Strange. Let's consider this possibility. Okay. Wait for Daniel, I mean. So, I will show you a little bit simpler example, but it doesn't matter. So, we have some variables S1, S2, and S3, and if we use just one thread, and in this one thread, this thread executes 3 for loops n times, every loop n times, n equals to 10 millions. So we'll see the time, consuming time, what it will be. Sections. So we can see that if one thread executes the same loop 3 times, and every time will consist of 10 million steps, that means our result will be 300 millions. So the answer is correct, and the work time equals to. Why haven't you said before? Because I can't see behind me.
Because I was understanding.
So S1, S2, and S3 is the result of some summarizing, and inside a parallel section, but in this case there is no any parallel section because I use just one thread, and this thread executes 3 for loops, one after another. And if one loop, so after every loop, the result will be 100 millions. And after this section, we summarize these results, and it will be 300 millions. So we achieve this correct result. And what about working time? It equals to 0.7, something like this. Now I want to use pragma-OMP sections. I use three threads. Command, and now I use sections, pragma-OMP sections, and each section describes every loop that was before. In the first sections there is this loop, and I use here local variables inside this loop, and after this loop I summarize S1 with this result and print that in the first section some thread works. Second section the same, third section the same, and that it was before I summarize results. It's frozen. Okay. Somehow my code I mean, I have made changes in my code. I save it, and it seems that why is it so? Why there is non-stable connection? Every time. So now we see that there are three threads inside parallel section, and inside parallel part of the code there is three sections. First section, and this first section is executed by thread number 0. Second section is executed by thread number 2, and third section is executed by thread number 1. So inside every section there is an answer equals to which one? Equals to what? Inside every section. Yes, 100 millions. And if we summarize these three results, it will be 300 millions. It's okay now, yes? But what about time? Yes. Yes. This time is less. Okay, what will be if I use not 3 but 4 threads? What will be? How do you think? If there will be 4 threads. Let's see. So it will be the same time, because one thread is just idle. Yes? And what will be, do you understand? Okay. And what will be if I use 2 threads?
going to be divided by 3 to the time, not 3 times less, but 3 divided by 2 times less.
3 divided by 2.
It's going to be 1.5 times less.
1.5, yes? So,
yes, I think so.
okay, this we'll see. I suppose the time should be approximately 0.4746, something like this. 47. Okay. Because in this, when we use 2 threads, we can see first section is executed by thread number 0, and thread 2, or I mean thread number 1, executes 2 sections. That means this time will be increased by 2, by 1 section after another. Okay, do you have any questions about sections? So using sections, you can execute some part of your code in the same time, and this part should be independent to each other. But inside every part, there can be some dependencies that cannot be parallelized, that cannot be divided. This is rather useful ability of OpenMP to parallelize something. And another ability of OpenMPI in command level parallelism, it is named as command level parallelism. There is a task. It is not so intuitive like sections, and maybe it will be rather complex. But we just familiarize. I just show you about this ability and what is it about. So this task directive is also should be inside parallel section. But if some thread executes some task, I mean task is some directive, that means this task is placed inside some pool of tasks. Okay, let's draw. For example, ID 0, ID 1, and ID 3. Let it be every thread executes some task. This task can be big, it doesn't matter. When they execute these tasks, that means every task is placed inside some pool of tasks. Let it be task 1, 2, 3. Task 1, task 2, task 3, maybe task something, a lot of tasks inside some pool. So after that, after placing tasks inside this pool, there can be idle threads or freed threads. And first freed thread takes some task, I don't know which one, maybe for example task 3, and executed by thread number 0, for example. Second, idle thread ID equals to 1 will execute task 1. For example, maybe thread number 0 finishes its work with task 3, becomes freed, and can take task 0. This is one situation. It can be another situation when thread with ID equals to 2 freed before, for example, this thread, and takes task 0. I mean task 2. Yes, it's 2. And so on. So what does it mean? There can be a lot of tasks inside this pool. And first freed thread takes some task from this pool and executes it. And so on, and so on. Every other freed thread takes another task and completes it. If it becomes freed, it takes another task, and so on and so on. So there are a lot of tasks, and every thread can take these tasks and execute. Okay? You can read about this once more. And there is some directive task wait just for synchronization. This thread which executes this task wait directive, it will do something after this directive only when its tasks were completed by other threads. It's a little bit complex, maybe difficult. I will show. So these are some examples. Have you read this?
Yes.
Some examples. It can be constructed like this. Some parallel section with 4 threads. And here you can see some OpenMP task. If there are 4 threads, so every thread pushes this task inside pool, and after that other threads, or even this thread, take some tasks from this pool and execute it. And here are some synchronization directive. Okay, we'll see how does it work. Maybe it's a little bit difficult. So this is a simple example without these statements. So here you can see parallel section, parallel part with four threads. Inside this parallel part, we can see part which executed by just one thread. We can use here if my thread, for example, or we can use here like pragma OpenMP single or pragma OpenMP master. It will be the same. So this part, I just show another possibility how to arrange part which will be executed by just one thread. So this thread will push this line or even this loop 4 times inside pool. Just one thread. This for loop is for time consuming, to let you see behavior of this directive. Just for time consuming in this example. But there are 4 threads. That means, okay, let's ID just one thread pushes task 1, task 2, task 3, task 4 inside pool of tasks. The same tasks. But now these tasks are visible for other threads. Something like this. Task 3, task 4. And if thread number 0 do something, I mean it pushes some tasks, at the same time there are 3 threads freed or idle. And these idle threads take some tasks from this pool. ID 0 takes, I don't know, maybe takes task 2, ID 3 takes task 1, ID 2 takes task, let it be, oh, not 0, we have not 0 here. Task 1, okay, let it be 3. And here maybe, so we have some free task 4 and it can be executed by I don't know which thread. Maybe at this point of time thread number 0 will be freed, will be idle. Maybe another thread will complete its operations and will be freed at that point of time. I don't know. So we'll see. But here you can see this statement. That means that this printf will be executed when all tasks of that thread under consideration will be executed. Because of threads 1, 2, and 3 never push any tasks inside pool, that means they are free and they will execute with this printf firstly, because there are no any tasks that were pushed by these threads. And there are 4 tasks that were pushed by thread number 0. That means, and because of the loop inside every task, it will take some time to execute these tasks. And that means this print will be executed by thread number 0 after other threads. That will be the last line in our terminal. So let's see. As I have said, threads number 1, 3, and 2 will execute this print firstly. After that, you can see that there are 4 running tasks by every thread. So every thread takes some task and executes it. When all tasks will be executed by all threads, that means thread number 0 will be at this point of time, pragma on task wait. All its tasks were completed, and now thread number 0 prints this line. We can see that this line are printed by thread number 0 after all prints before, something like this. So maybe it is rather difficult, but this approach can be used when there are a lot of some tasks and you do not know what they are, but they should be, of course, independent to each other. And maybe these tasks created not at the very beginning of your program, but during your program. And when this some task is appeared, you can push these tasks inside pool, and freed thread can execute this task. When, for example, several seconds are gone, and again some tasks appeared. These tasks from your algorithm, I don't know. And this task can be pushed again inside pool and so on. And freed thread can execute this task from the pool, something like this. So it is just to be familiar with this approach that now you know that this approach exists inside OpenMP, and it can be used to parallelize some part of your codes that can be dependent inside this part, but these parts itself themselves can be independent to each other, and so on. It's similar to sections, but mechanism a little bit complexer. Okay.
Should we have a little break?
Yes, of course. 2 minutes, and that's all. It will be a ring. So, do you have questions? Do you understand or not? Or this is?
I mean, I understand, sir, but I think I need to run this home, so see like to play around with the code a bit. So I think that's the best way to understand things. As for like the main idea, yes.
Okay. Other persons? You do understand? Ashish, Ron, Krutika, understand?
What does everything do?
Huh? Revise? What we? What? Ah, I see. Okay, so I put the examples, code examples, inside our group, Telegram group, and you can try it by yourself and so on. Okay. Okay, let's make a break.
Are we working now on the homework? Okay, this is the when we work and we ask the questions.
But firstly, I want to complete because there is one useful issue I want to discuss. This issue consists is about combination of MPI and OpenMP. Because contemporary clusters are rather complex machines, and they consist of some nodes. Every node are connected with a network, and we have to use MPI to use all nodes inside these clusters. For example, if nodes in this cluster are single core machine, that means this cluster is for MPI only. So in this case we have to use MPI and that's all. But if nodes of this cluster consist of shared memory machine, that means we can use MPI to distribute our data or our program between nodes, and on every node we can use OpenMP to use threads to parallelize this part of the code inside every process once more. So how it can be shown? Like it was in MPI, there are several processes. Let it be 3. For example, if there exists existence of 3 nodes in the cluster, and every node is a single core machine. That means we can use just these 3 nodes and 3 processes. So we use 3 processes. But if 3 nodes and every node is a shared memory machine, and let it consist of 4 cores. That means on every node we can use 4 threads. Don't we? Where are you looking all? You all looks on your screens. What did you find inside your screens?
I'm just preparing to show the homework.
Okay, let's prepare a little bit later. I want to show you something interesting things. So maybe these things are not interesting for you.
I'll show you links.
Okay, what I was speaking about.
So you said 4 threads per node, that's less than it says.
And Ron, what will you say? How do you think what I was speaking about? Okay, and what I was speaking about?
Yeah, I was looking at the screen.
So give me -1 point for the whole semester, basically. That's what you
Maybe even 2. I don't.
The more the better.
And Ashish, what do you say? What can you say about what I was saying about? Okay. So how we can use all the power? We can use all the power of so complex cluster. We can divide our program or data into 3 parts. 3 processes mean 3 parts, and inside every process we can use 4 threads. 4 threads.
Can we increase the amount of threads to make it 5 or 6, or it's constant 4?
We can, but there will be no time speed up. I mean, there will be no speed up, because speed up will be when we use number of threads equals to number of cores. So if we something like this, especially when we deal with some numerical tasks, that means there should be several for loops inside every process with independent data. In this case, we can divide every loop inside every process into parts, and the number of these parts will be equal to number of threads. The scheme is like this. So I want to show some simple program. By the way, this simple program is your first program and fourth program to calculate some integral. The beginning of this program is almost as it was in the first program. MPI, and you can see that I use MPI functions. But at the same time, I use some OpenMP functions. By the way, because nodes in the cluster are down, I cannot show you how to use Slurm to launch this program, OpenMP plus MPI. So I will launch this program just on the client machine. And because of client machine consists of 4 cores, we cannot use more than 4 processes and so on. I can use, for example, 2 threads and 2 processes, and we'll show you the speed up on the client machine only. So we can see, you can see that I use OpenMP functions and MPI functions also at the same time. And I divide, firstly, I divide my, how to say, number of iterations, something like this, like it was in MPI program, into parts. This in parts, and the number of these parts equals to number of processes first of all. Yes, you can see if size is the number of processes. I divide my number of intervals, okay, into parts. Process number 0 sends these parts these numbers, I mean, no, these numbers to other processes. Other processes receive their chunks, and here I use OpenMP code. So now every process has its chunk, so it's number of its intervals. And now we can and to calculate its result, I use, or this process use some for loop. And you can see this statement inside for loop. Okay, statements in every step of this loop are independent to each other, and that means we can divide it or we can parallelize this loop using OpenMP. So I create parallel section, and inside this parallel section I use directive pragma OMP4 to compute this part of integral in this process using for some threads, some number of threads. At the end of this parallel part, every process calculates its part of the integral and sends this part back to process number 0. The process 0 receives and summarize. Here, summarize and print the answer. And I use an WTime function of MPI measure the time.
What is begin for every thread?
Huh?
What is the value of begin for every thread?
Value of what for every thread? Begin?
Yeah.
Begin, I send begin from 0 to other thread, to other processes.
So it's different for every thread. Begin is different for every thread.
Begin is different for every process, by the way. I move this begin. If I no. I divide my scope of definition between processes, and here every time every begin for every other process, and this is chunk. Okay, we'll see. So to compile, why is it so every time? Where is it? So you can see that all nodes in the cluster are down, and I use only why is it so every time? So the connection is very unstable, very. Can't print anything. So to compile this gibberish program, gibberish, because it contains MPI functions, that means I should use MPI CC, for example, MPI OpenMP, but at the same time I use OpenMP, minus F OpenMP. Now I have compiled it, and now I should use which command to run MPI program. MPI run or MPI exec, doesn't matter. Okay, minus NP. Okay, let it be. Firstly, I use just one thread. One thread and one process. Let's see. Compile once more. And MPI run minus NP 1. Okay, here I print what I print. In parallel part here, in parallel OpenMP even part, I print number of process and ID of process and ID of thread and number of threads. So we can see in parallel part there is just one process and there is just one thread. Result is correct, and time of calculation is 3 seconds. Let's use 2 processes and 1 thread. It's frozen. Because there is no connection.
I think you should tick that box so that it connects automatically every time.
Okay. But you see, result is correct and the time of calculation is 2 times less because we use 2 processes, process number 0 and process number 1. Yes, and you can see that in every process there is just 1 thread.
So do you know when the nodes are going to be fixed, or there's no date yet?
I don't know.
But the question is, if the nodes are not going to be fixed and the people have to draw the graphs, what will be the outcome that they won't be able to fix it till the end?
If there will be, if the cluster will not be fixed, that means this is not your fault.
So we're going to get marks.
Of course, maybe you try to use just client machine for threads or for processes. That's all. What we can do, we can do the best. and MPI MPI OpenMP minus F OpenMP MPI run, and now I want to use one process and two threads. So 2 threads and one process. And one process, MPI run minus NP, one process and 2 threads. It looks strange, by the way, because if there is just one process, we can, this for loop statement should be parallelized. Okay, let's use 2 processes. 2 processes and 2 threads. We see there is a speed up. In this case, yes. So when we use 2 processes, but there is something, maybe, I don't know, maybe it's because of the clone machine. Maybe. Because before I have launched using all nodes outside client machine. And where is it? This statement should be like this. Number of nodes. Node is a big one. For example, n tasks per node equals to processes, number of processes. And CPUs per task. That means number of threads inside every process. So number of tasks, and every task will be completed or will be executed inside number of CPUs. And so 2 times 2 will be 4. 4 instances to execute your program, something like this. But now we can't launch this Slurm. We can't because all nodes are down.
How can a water leak happen in the nodes cluster place?
About leakage?
So as I understood from the message you sent, like there was some water.
Yes.
How can water get in there?
Because there is a circular motion of coolant inside machines.
But why not a fan? Isn't fan better and more safe with the thing?
No, there is these computers rather powerful. So, as I understand, as a coolant it is used. I don't know. Maybe not water. Water is not so good for these things, but some liquid.
So it's just like there's like I think some alcohol which cannot make a problem with the circuits, like isopropyl alcohol. If it's like 98%, it should not cause a short circuit. Like why don't they use that?
Yes, I also thought about this some kind of liquids without electroconductivity.
Yeah.
So I don't know.
Somebody lost their job probably. It's a big, like I think it's gonna cost lots of money to fix such a big server, I think.
So we have to wait, or we have to use what we have. So I think now is 29th of November, and from my point, I think I have said what I wanted to say. And now we have 3 or 2, maybe 3, maximum 3, I suppose, classes to do your homework, to make changes and to finish your homework, to show me and to take marks.